Hi, my name is Carsten, and this is my presentation for the Symposium of Rising Scholars. This slideshow will cover my recent research project titled How Do Various Fin Profiles Affect Aerodynamics in Model Rockets? When I was younger, I would always get super excited when our family announced that we were going on a vacation. But I wasn't excited to visit the beach or play on top of a snow-covered mountain. No, rather I was excited to go to the airport, jump on a plane, and view the Earth from above the clouds. If you ever ask me, you'll know that I'm a window seat person, not an aisle seat person. My name is Karsten, and I'm 15 years old, and for as long as I can remember, I have always held a burning passion for taking flight, rising into the sky, and then going even higher and exploring the planets and the stars. When I was in 8th grade, I discovered model rocketry, and I began to not only act upon my passion, but also sharpen my engineering skills. Today, I hold a junior high power level 1 certification and only wish to continue advancing. However, in addition to my passion for aerospace, I've always loved the idea of researching a specific topic and then sharing my results with others who share the same passion for aerospace that I have. So of course, I acted upon this passion too, and I decided to research the aerodynamic effects of model rocket fins and write about it. And this is why I'm here at the Symposium of Rising Scholars, to share the results of my research further and act upon my passion. Now, I'll cover what I am researching and what I am aiming to achieve with my research. One of the most essential components of a model rocket is the fins. Without the fins, a rocket's flight path is unstable, unpredictable, and dangerous. Thus, it is essential to incorporate fins into one's rocket design. If you look around online, there are many different fin shapes and profiles to choose from. These fins all serve the same primary purpose, that is, to keep a rocket stable. But they can also have secondary purposes such as decoration or aesthetics. Additionally, any two distinct fin designs will impact the rocket's aerodynamics differently to some degree. For example, one fin design may produce less drag, while the other fin design may produce more stability. This is what I want to research. I will be experimenting with these different fin designs, testing 4 common fin shapes and 3 common fin cross-sections. The 4 fin shapes I will be testing include trapezoidal symmetrical, trapezoidal delta, trapezoidal swept, and elliptical. The 3 fin cross-sections I will be testing include square, rounded, and airfoil. I aim to determine exactly how these designs affect a rocket's aerodynamics, and arguably more importantly, why exactly these designs cause these effects. Before the experimentation process, I needed to first hear about what others had to say about this topic. I found 2 main claims that most sources seem to follow. The first claim is supported by Tim Van Milligan, the face of Apogee Rockets, one of the most popular online rocket source and an incredibly reliable source when it comes to model rocketry. This claim is also supported by 2 other research studies done at the California Science and Engineering Fair. It states that trapezoidal symmetrical fins result in the lowest apogees and elliptical fins result in the highest apogees. Van Milligan argues that when trapezoidal fins generate lift, pressure differences around the tips of the fins create vortices, which generate induced drag, which pulls the rocket down. Elliptical fins don't have this problem due to their curved shape, which eliminates these vortices. This justifies why Van Milligan and these studies support this first claim. The second claim is not supported by people, but by running computer simulations on various rocketry software. This claim also states that trapezoidal symmetrical fins result in the lowest apogees, but unlike the first claim, this claim states that trapezoidal swept fins result in the highest apogees. This second claim is backed up by the fact that trapezoidal symmetrical fins are nearly perpendicular to the airflow, but trapezoidal swept fins are nearly parallel to the airflow, allowing air to collide with them less violently, thus creating less drag. This justifies the second claim. But what do I think? What is my hypothesis for the upcoming experiment? Personally, when it comes to which fin shape performs the worst, I would have to say the trapezoidal symmetrical fins. Not only do both claims support this statement, but it also makes logical sense that the trapezoidal symmetrical fin's leading edge, which is nearly perpendicular to the airflow, would produce the most drag. When it comes to which fin shape will perform the best, however, I would have to agree with the second claim, which states that trapezoidal swept fins perform the best. I feel like the leading edge's angle relative to the airflow, which is called the sweep angle, is so much more of a determining factor than induced drag. But what about the fin's cross-sections? Only the second claim has something to say regarding fin cross-section, and it's that square cross-sections result in the lowest apogees, airfoil cross-sections result in the highest apogees, and rounded cross-sections land somewhere in between. I would have to fully agree with this statement because rounded cross-sections and airfoil cross-sections cut through the air much more easily compared to square cross-sections. Additionally, airfoil cross-sections reunite the divided airflow the easiest due to their tail-like trailing edge. To summarize my hypothesis, I think that trapezoidal symmetrical fins result in the lowest apogees, trapezoidal swept fins result in the highest apogees, square cross-sections produce the worst results, and finally, airfoil cross-sections produce the best results among the three fin cross-sections. One of the preliminary processes of experimentation is defining the test apparatus. The test apparatus includes all the details about each variable of our experiment and how it will be modified or recorded. The first detail about my experiment that I want to outline is that though we will be testing 12 distinct fin sets, since 4 fin shapes times 3 fin cross-sections is 12, we will not be building 12 rockets. How is this possible? Well, I've created a solution using 3D printing that I call a fin rail. It allows fins to be quickly dismounted and replaced onto a rocket within seconds. I have attached some images to the slide which should help illustrate how this fin rail idea works. Thanks to the fin rail, I only have to build 3 rockets, 2 to be flown and 1 as a spare, with each rocket containing 3 fin rails. But what about the rockets themselves? What are their specs? All 3 rockets are identical, built with a 12-inch BT50 body tube, a PNC 24C nose cone, and an 18 to 24mm motor adapter, just to name the most important parts. Additionally, all 3 rockets fly on an Estes C6-5, and they also record their data using a Jolly Logic altimeter too. Now that our test apparatus has been fully defined, it was finally time to experiment. Here I have attached several images of our experiment day. Following the experiment day, we began to analyze our results and findings and determine what we got right and wrong. 2 things that we got right were the best performing fin shape and the best performing fin cross-section. We accurately predicted that the trapezoidal swept fin shape would perform the best out of all the fin shapes, and we also accurately predicted that the airfoil cross-section would perform the best out of all the cross-sections. On the other hand, we failed to accurately predict the worst performing fin shape, and we also encountered a strange anomaly that we did not expect, that airfoil cross-section fins have no pattern in performance whatsoever, no matter the shape of the fin. We suspect that the reason for the first inaccuracy, that elliptical fins perform the worst, not trapezoidal symmetrical, is due to the larger surface area, and thus the higher weight of elliptical fins. Even though the difference is small, the elliptical fins we 3D printed did have a slightly higher mass. The second inaccuracy, that all airfoil cross-section fins, regardless of their shape, have no pattern in performance whatsoever, may be a result of low speed. None of our rockets exceeded 170 miles per hour, and since drag increases with the square of velocity, the amount of induced drag each fin shape created was negligible. Thus, the difference in apogee between fin shapes and with an airfoil cross-section was minimal. To close, we researched different fin shapes and cross-sections and determined how they affect the aerodynamics of a rocket. We started by researching this topic online, then giving our own thoughts, and then executing our own experiment in the real world. And finally, we analyzed our results following the experiment and gave our thoughts on why various anomalies occurred. From this research project, I have learned many things. One of the things I learned was that some things cannot be replicated unless they are done in the real world. None of the sources I found online or the simulations I ran seemed to match the actual outcome, and I would have never come to that if I had not decided to do this experiment in real life. With that, I'd like to thank you all for your time. Thank you.